So, when I was a young engineer, a young student, I was trying to order some motos. So I thought, yeah, buying moto, right? Anybody can just go shopping and buy a moto. So I call up the company, and the company asked me, okay, moto, what moto do you want to buy? And I was like, well, I just need something to move, yeah. Without knowing much about the huge array of motos out there. So I ended up sounding silly. I didn't do my homework. I tried to buy something that I don't even know. Don't let that happen to you. So today you have a look at the various different types of motor. It's not going to be exhaustive. Yeah, seriously, a huge array of the various different motors around. But what I thought you should know is some of these basics. So we'll be looking at four main types today: the brushed DC motor, the brushless DC motor, the stacker motor, and PMAG, permanent magnetic AC motor, or sometimes it's just called AC motor. So if you have been wondering why are there this huge array of motors, because motors is not invented just one day. It was improved over a long period of time, and as they improved, they discovered that this thing is not doing what they like, so they redesigned it, and out of which they find that that new design is good for something and the old design is good for something. So what is that something? Before we jump into that, I think it's good to review a little bit about the basics. Your left-hand rule. Now, there's a difference in motor and a generator, so you need to make that distinction. A motor is when you supply electricity and it runs. The generator is the other way around, it generates electricity. That means you provide the motion and then it gives you electricity. So these two devices uses two different hand groups, left hand group, right hand group. So the motor can go for the left hand group. So this is an example of that. In this figure, you have to see, I think at the time I brought in the wire frame. This wire frame over here. So actually some of you found it hard to imagine, because I guess it's a little bit incomplete. Yeah? Because what I didn't show you is that there is two parts over here. It's like a ring. This ring, while it's connected to this wire, they are not connected to each other. So it's kind of like an arc-moon shaped ring. So as this wire frame were to rotate, the ring will rotate. So what is attached to this ring to the rest of the circuitry is this part. Two sides that we call brush. So brush would be kind of like a contact point. A brush is not a brush. It's not soft, that type of brush. It's just made of carbon. So the carbon is able to slide across solid surfaces. So in this case, this ring, there's a special name for that. It's called commutator. There's one year that some student wrote computer. It's a different word. Computer and commutator. Commutator is this device. So there'll be two brushes by the side, and the brushes go right, while your wireframe here will. So you can see that let's say on this side there's a brush that's touching it,
And as this wireframe would rotate, this is how, and then you go to the other side of this wire once it touches already. Later on there'll be a figure so it allows you to realize that. That's what it's going to be here. You have the brush that's touching one side of this commutator, and as the whole structure, whole wireframe would rotate, and it would touch the other side of the wire. So giving it that the alternating touching of this wireframe. So how does the current flow? Since it's going to be a motor, so the current will be introduced. Let's say over here, you will go this way, and then it's going to go that way. Correct? One complete circuit. So if you use your left-hand rule, so I think you can do it in the air. So this finger over here is where your north is going to go to the south pole. So in this case, it's going to be that, right? And this finger over here is for the current. Okay. So try to position yourself such that, yeah, you go that way, right? The current is going up. So then you get the motion for the motor. So the motion says that this part here is going downward. And your current will flow to the other side, and over this side, the same thing, right? Your field is still going to be there, and your current now is pointing this way, so the force is pointing upward, right? And with that force is pointing downward, this one is upward, so you get the wireframe rotating. So as it rotates, you would lose its force. Why would it lose its force? That's because this magnet here is only magnetized in this region. So as it rotates, it's going to get lesser and lesser magnetic flux. With lesser magnetic flux, the amount of force that's generated will be lesser. So, but its momentum is going to kick it. So you will turn, you will swing, and then you will come back to that. So what it had previously, that current direction. So if I were to use this over here, yeah, these two directions. So if this one were to go up, and that one were to come down, this current direction now will be flipped. That one will be flipped. So you can see that your current that's applied to it is not changing. It's just constantly supplied because now that side that used to be here now comes here, and that current will flip because of the commutator. Like that. Current is always applied in this blue direction. So this is what we call the this is the basic principle of the motor. So you could see that there is this correlationship between the amount of force that's produced has a correlationship between your magnetic flux, right? So this flux is magnetic flux density measured in Tesla. Usually that amount of Tesla is quite small, and it's also proportionally equal to current. So the higher amount of current that you supply, higher amount of force. So if you want to design a motor, so you need to have strong magnets. And after you have strong magnets, the motor you need to supply electricity, so high amount of current. So you get a lot of force. And if you want more force, then you extend the length of your wire. So the length will be provided by that. That will be L. The longer that length, but that length got to cross over the surface area of your magnet, right? So they got to match. So if you have long length and long magnets, providing the north and the south pole. So those are the things that will govern the amount of force that you can obtain. So these two forces, they are actually equal to each other, right? At any point of time, they are equal to each other. And because they are rotating, so you get a resultant torque out of the force. So that's why when you fix your load to your rotating motor, you'll get a certain amount of torque. And if you want a larger amount of torque, those are the things that you look at to increase your magnetic flux current in the loop. So because of the commutator, so it's able to continuously rotate without the need to change in the current direction, because inherently it's kind of like changing by rotating, and the current will actually change. So in practice, this commutator and brushes, later on actually there's a picture over here. This commutator and the brushes, they're actually used to change the current. Now this is a static one, so if you were to rotate, you can see that this part here, now if it rotates to the other side, then this part here will be touching this part here. Okay. There's another type that's called brushless, so later on we'll be having a look at that. There's also, if let's say you prefer not to have a split commutator, what you could do is to have one single ring commutator, but this ring is actually independent of each other. So you have one ring, is going that way, and there's another ring inside, and then there's this brush, and there's that brush touching that ring. So they're not touching each other, but how can we make sure that they can still rotate continuously? We provide alternating current, so this is also possible. So if you want to apply a constant current, then you use a split commutator. If you use alternating current, that means your AC current, that will be the change in the direction. Current at one point of time will flow clockwise, the other time it will flow anti-clockwise. So in that case, then you wouldn't have the need to split up your commutator. So it's just a different kind of design. It's known to be that the brushed DC motor, and brushed because there's a brush over here that's made of carbon. They are reliable, sturdy, powerful. There are some terminologies that I want you to know. This magnet over here is known as the stator, right? So it's a specific word, stator. And the one that's rotating naturally is called rotor. And usually the rotor, in this case of a brushed DC motor, is a coil of wire. And because it's a mono, that's why you have this DC power supply that's attached to it. Now this is a good view of what a real DC motor is going to look like. Now why it became like a lot of these lines over here? That's because if I have to focus on just this figure.
So if you look at this figure, what had been improved just now was that the stator was flat, like a block of a magnet. And now this stator is arcing. And there's a good reason why it's arcing. When it arcs, the north and south pole, it's always going that. So it's good to arc that. In fact, the magnet is not built in a block with this cut, but it's actually built as a arcing kind of magnet to provide the north and south pole. So that at any point of time when this wire frame would rotate, it's always experiencing the magnetic flux that's cutting through it perpendicularly. So this design is still not good enough. We can improve it further. Why do I need to just loop one time? I want to use the same strength of wire, loop it a lot of times. Right? If I can loop it a lot of times, then at each time that force kicks in, I'll have a lot of strength of that wire that's experiencing that force. Right? Have a lot of torque. But then when I do the coil, it's not going to coil just this plane over here. I don't coil it in this plane. I coil it in this kind of plane. Right, so there'll be one coil that will go here, here, and then the next coil it will go there, 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 yeah. So I'll coil it in that way. So you can see that at any point of time, a lot of strands of wire are experiencing the amount of force. Right? So this is good. So the current would just flow within it in that direction. And you can see that the stator now is arched in that way. And we still have that commutator that's over here. This part here is a commutator. And then your brush, right? This thing is a brush. It's touching it. And then the rest of it is connected to your battery or your power supply network. The stator at the outside. So this is how the DC brushed motor is going to look like. Actually, DC brushed motor is quite sturdy, and the amount of torque that it can supply is tremendous. So let's have a look at some mathematics. How to model this brushed DC motor. The amount of torque that we can obtain relates to the amount of force that's being generated. And that amount of force that's being generated is proportional to the amount of current that we fit in. In short, under a constant flux, magnetic flux, if this is constant, then as we increase the current, the amount of torque would increase as well. But there's a limit to the amount of current that you can put through a motor. If you have heard before, oh, my motor burned up, the likely culprit is that because there's too much current that's going inside the motor. How did that happen? The large amount of current. Well, that's because when you try to drive, use your motor to drive something, you find that, wow, it actually couldn't move that thing. Let me give it more power. That more power gives it more current. And under a higher amount of current, if it's not within the design spec of that motor, it's going to melt down, it's going to burn your motor. There'll be actually some early signs of that. Now, usually you smell it first. If you smell that burnt smell, please don't turn more power to the motor because that burns it faster. So there's a torque to current relationship that's governed by KT, and KT here is called your torque constant. Alright, and it comes about because KT, okay, I'm going to write capital letter K in this way. KT is equal to small letter k, T, 5. So what I'm going to do is to do a sketch of a motor schematic. So the schematic of a motor can be drawn in that following way. You see that the following slides is very similar to what I'm going to be sketching. So you could look at the slides and fill in the gaps, or if you want to write after me, you can choose to do so as well. So your motor would have a certain amount of resistance and certain amount of inductance.
And this is a symbol for motor. It's not a TIE fighter. And the amount of voltage, V, that's applied to the motor. And the inductance, I call it L. The resistance, I call it R. And there's this current that will flow through the motor. Now,
Actually, for DC motor, there's something strange going on as well. Because I was talking about a motor, same construction. If I supply electricity, it will rotate. The force will be generated. Using the same motor, if now I were to rotate it, I actually could generate electricity. So there's this thing that happens. Two things at the same time. When you supply electricity, you let it rotate. That rotation itself will actually generate electricity. That electricity that's generated is in the opposite direction of what you have generated, what you have supplied. So that amount of voltage that has been generated is called back EMF. Just so because it's rotating, and because it's rotating, it's also generating the voltage, and that voltage is in the opposite direction. And that's what we call the back EMF. So if you have heard about back EMF before in earlier applications, that came about just so because your motor, you are also using it as it turns, it's also behaving like a generator, and is providing that back EMF. So that amount of back EMF
represented by this. So back EMF is its units is in volts. So we could formulate an equation for back EMF E. It's given as kV phi omega, and I'll define them. Your kV is it's just a constant, right? It's just a number. This capital letter kV will be your torque, constant. The phi over there, that is your magnetic flux. Your E there is your back EMF. And your omega over there will be your angular speed. So you can see that the higher that angular speed is, the higher your back EMF is going to get. That's one equation. I'll call it equation 1. To relate the amount of torque that's being produced by supplying the current to your motor, torque will be equal to kT, small letter kT, phi I. And I'll define those as well. Your T here is your torque. Your kT, small letter kT over there, that is again a number, constant. Phi, again magnetic flux. I, obviously, is your current that you apply. And this capital letter K, KV, where did it come from? This whole thing over here is actually capital letter KV, omega. And I call this equation 1. And this whole thing here, I call it capital letter KT, I. And I call it equation 2. So your capital letter KT is also called torque, constant. So back EMF relates to the angular speed, the torque that's generated after you supply the electricity is related to the amount of current that you supply. So what I'm going to do is to say that if V, this V over here, is called our applied voltage, then I'm going to relate that voltage as in using the Ohm's law, V is equal to IR, whereas in this case, that V, you must minus away the back EMF equal to current multiplied by resistance. And we could simplify this. I equal to V minus D divided by R. And what I'm going to do is to replace that E. So V is equal to minus KB omega, and then divide by R. And what I'm going to do is that take this equation to substitute that into equation 2. So my equation 2 is over here. So I get a torque expression, T equal to KTI, and then I'll start to replace that I as V minus capital letter KB omega divided by R. So I can take out that denominator R, just check it out, KT over R, V minus KB omega. And what I'm going to have, if I multiply term by term, KT V over R minus KT KV divided by R omega. So a torque expression that relates to the rotational speed.
Now this expression is interesting. If you look at this part over here, the amount of supplied voltage is a constant. The torque constant is a constant. The resistance of your motor is a constant as well. So that part is a constant. The same goes for this. It's a torque constant. KT and KB happen to have the same name. They are both called the torque constant, where your KT relates to your torque, and then your KB relates to your back EMF. This is also a constant. T equal to constant minus constant omega. What kind of? If I were to sketch this in the axis T versus omega, what do you think I would get? In this axis is called T versus
Omega.
What do you think I would have?
Do I get a straight line or a curve? Get a straight line. How's that straight line going to go? Which way? This way or that way?
This way.
Yes.
That way, right? This equation is just like y is equal to minus mx plus c. Alright? So that part there is your gradient. That part there is your y-intercept.
So it's going to look like this, going down at a certain gradient. So this gradient over here, gradient is minus KT KV over R.
And this
Y-intercept over here, that will be your KT V over R.
So there's one thing that, because now I've
establish a relationship between torque torque that's provided by your motor to its rotational speed, angular speed. Now, if I were to increase the voltage supplied to my motor, how do you think this line here is going to behave? Increasing voltage, V. Is it going to have a different gradient? Because gradient don't have V in there, so it's not going to affect gradient. So if gradient is not going to be affected, as you increase V, will this line be somewhere higher or somewhere lower? Yeah, it will be higher. So that's your direction. Over here. So this arrow, I'm going to say that is for increasing V across the motor. So the more that you increase, the more this line would go up. There are also a couple of interesting things. So in your lab, robotics, Lego lab, where you start to toy, you get to experience a lot of motors. So you sort of build a robotic toy and then write a report about it. As you play with the motor, you discover that there's this play between torque and speed. And you very quickly discover that you actually get higher amount of torque when the speed is low. Preferably no speed. That means before if you were to kind of like put your hand and squeeze on the shaft of the motor so that it doesn't move, you can feel quite a significant amount of torque. And the other spectrum of it, when you have very high rotational speed, angular velocity, that omega, you find that the amount of torque that you have over there is very, very low. In fact, so low that it can be almost zero. So this line over here describes that. When omega is equal to zero, when there's no turning velocity, you can experience a high amount of torque. So high. In fact, this torque over here is what we call T0. We call it the stall torque. Stall torque at the condition when omega is equal to zero is given by this. So this one here is stall torque. What does stall means? It just means that you have energized your motor and then you kind of like stop it from moving by pressing on the shaft. But you can, in your thumb, feels that it's trying to turn. That is that stall torque. No velocity, but you can feel that there's a torque. Right? At the other spectrum of it, this is when there is no torque. Right, over here, you have a lot of velocity, angular velocity, but there's actually no torque. So that's where you get to hear a lot about, yeah, if you want torque, then you have to sacrifice your velocity. Or if you want to have very high velocity, high speed, then actually that high speed couldn't give you a lot of torque. Right, so this is the line that describes that. Mathematically, how do we see it? Since we have the equation of that straight line, let's have a look at this condition where we were talking about stall torque, where we have maximum amount of torque with no shaft rotation. Right, there's no shaft rotation. So if that's the case, that means what we're going to have is when there's no shaft rotation, this term here is going to be gone. So you have T equal to K V, KTV, R minus KT KV over R, and the omega is 0. So this term is gone, so we say stop torque is equal to KT V over R. And the other spectrum of it, when there is no torque, that is at maximum angular velocity, omega. So in that case, when there is no torque, so that T term will be equal to 0. You have the rest of it. Omega. So there's a common factor, KT over R, KT over R. So that one I could take it off by kind of like multiply R over KT throughout. So you get that. So that leaves me with an expression, omega is equal to V over KV. So this omega here would be the maximum speed, maximum velocity, or sometimes it's called no load speed. Yeah. What is your no load speed? So that's kind of like your maximum speed. So if I were to adjust this a little bit, I'll get KV omega equal to V. And this is actually equal to the back EMF.
So what is this saying is that as you rotate it onto a certain speed, at a very high speed, that is when the amount of back EMF that's generated equals to your applied voltage. That's why there's no torque. Right. That's what it means over here. Because now this KV omega, isn't that, if you look up earlier, that's equal to your back EMF. So now your back EMF will be equal to the voltage that you apply. That's why at that maximum velocity, there's no torque that you can derive out of it.
So that gives you an outline of that torque and rotational speed relationship. So when you go about designing your Lego toy, you must discuss things like that in your report. You'll find that how can I have a lot of torque and a lot of velocity, and you just couldn't have both of them because of this relationship. So that was brushed DC motor. Your Lego toy uses brushed DC motor. The motor that's in there is brushed DC motor. There's another version that was invented that's called brushless DC motor. Now, if you want a copy and haven't finished copy, no problem. During break, you can come to me. Just open it up and you can do the copy. Let's have a look at brushless DC motor.
So the brush DC motor I was describing, there's this brushes that's beside you, and this brushes, although it's made of carbon and it can last a long time, over time it's gonna wear off. So that is a problem, right? And also, even though it's made of carbon and
the commutator can slide over it smoothly, you experience some bit of friction as well. This is undesirable. And there's another thing that's undesirable about brushed DC motor is that if you want it to run high velocity, you got to supply the amount of voltage to it at a higher voltage. You'll quickly find that you will heat up substantially. That's one of the drawbacks of a brushed DC motor. So then we come about designing this another kind of motor that we call brushless. Why is it brushless? Well, that's because there's a brush in there. So why is it that it's possible to work without brush? That's because we inverted the concept. Just now you heard that the stator has got a coil of wire inside, and then not the stator. The stator is your magnet, right, on the outside, and then the rotor you have the coil of wire. So brushless DC motor inverts this. You have the outside that has the coil of wire, and then the inside that is your magnet. So what's going to happen is that your rotor now, the thing that rotates, is your magnet, permanent magnet. And then what is out there is actually your stator. So then how to introduce the coil of wire in this outer stator? You can have, in this minimum scale, two circuitry. The first circuitry is this one over here, and connect to the other one. Right? So these two guys here, they are paired. And they are paired such that one side will provide north when it's energized, and the other side will provide the south pole when it's energized. So if you imagine now, if I were to energize this as south, and this one is north, this rotor, that north, is going to get attracted to the south in that way. Right? So at the same time, what I'll do to that one, I'll provide a north, and then this part as a south. So you will repel it. Right? So that rotor will get repelled because it'll be north, north, south, south. This one here, it will be south, this will be north. So you can see that this rotor over here is highly attracted to rotate to this position. Right? So now it's just a matter of timing these two sets of coils such that you get a continuous rotation. There's no brush involved. In fact, this one will give you very little amount of friction. The amount of friction that's going to come from is where you're going to be supporting your rotor over here in that axis. So then how do we go about doing that timing? We use this thing, these black dots over here. These black dots are your Hall effect sensors. Do you remember Hall effect sensor? How do you trigger the Hall effect sensor? In the presence of how do you trigger your Hall effect sensor? You must bring it near to, you must bring that something near to it. Whatever is that something? Magnet. So that's why over here, as this rotor would flick over here, in the presence of magnet, it would trigger it. So you use that triggering signal to say that yes, I can sense your rotor magnet has now come to me. Alright? And that will provide that timing signal. So this is sort of like a microcontroller. So after sensing it, then you'll provide that triggering to activate north and south poles to each of these coils to provide that continuous rotation. There's also one hidden advantage for brushless DC construction. Now, just now we were talking about the brush DC motor. If we want to run it hard, we supply more current, more electricity to it. And in that process, it will get heated up. So if it gets heated up, that's heating it up, that brushed DC motor inside of it. And in this case, because the coils are on the outside of this brushless DC motor, disadvantage. This is why so? But that's just because if this coil were to get heated up, this heat can get transferred out of the brushless DC motor much more easily compared to if the coil of wire were to be in the core as the rotor. So if it's in the core and in the rotor, you can see that how heat is going to transfer out. There's this stator, there's this coil, there's this air gap in between. So heat would need to transfer out through that air gap, through that stator, through the shell of your motor, out in the atmosphere in order to get cooled down. That means internally, for a brushed DC motor, gets heated up without the ability of heating down. But this configuration, brushless DC motor, even if you get it heated up, the heat can get transferred out. The only thing that is stopping it is that metallic shell of your motor. So it can get transferred out. And hence, you get cooled down. That's why it's cooling down such a big deal. That's because if it can cool down, that means I can give it more, a larger amount of power. And hence, your brushless DC motor can actually accommodate higher amount of current. Higher amount of current means that you can get a larger amount of power. Stack a little bit more, squeeze out more juice out of it. This one's talking about the brushed DC motor. Sometimes if you get to see some sparks, that's coming about it. Your brushless DC motor will never introduce sparks. And then because of that commutator and your brush wearing, so you suffer a severe wear. That's why brushless DC motor is more attractive. I think this thing spoke quite a bit about what I was trying to say. High reliability, low maintenance. This is how a typical brushless DC motor is going to look like. So you have the coil at the outside, and this part over here is your stator coil, and then your inner rotor that's made of magnets. So the operation, because there's no brush, is pretty quiet, and you can operate at very high speed because there's very little amount of friction. And that was the one that I was talking about. It's easier to cool compared to the rotor. And this figure over here talks a little bit, talks about having a three-phase brushless DC motor. So just now when we were talking about using the Hall effect sensor to time it, there are some other brushless DC motor that doesn't make use of Hall effect sensor because they are actually quite expensive. Your Hall effect sensor, they are a few dollars only, but if you mass produce, it's expensive in manufacturing line. So what they do is to introduce 3 coils over here, and the smart thing about these 3 coils is that they are energized sequentially without using any Hall effect sensor at all. So this is a minimum scale of things. I have 3 coils, one over here, the other one over here, the other one over here. And what I'm going to do is to energize them. Energize means making it magnetic. So energizing it sequentially. Alright? And sequentially means that I have this one that's energized first. So if it's energized to be a north pole, the south will be attracted to it. And then I next energize the other coil, make it a north pole, and then this south will continue its journey to get attracted to it. And then I energize this one
as the North Pole and the South should continue to get attracted to it. So you have 3 coils, and these 3 coils would have 3 waveform of current. So what it means is that
This one will oscillate this way, and then this one will be 120 degrees out of phase, and this one would be 240 degrees out of phase. So if I can energize it that way continuously, right?
by supplying this sort of AC current to it for these 3, you can see that the permanent magnet in the rotor will just continue to rotate, right? So that's why there is this 3-phase that you always get here, 3-phase. We don't have a 3-phase in an FYP room, but if we have it, you'll be able to generate a lot of torque. And this is one of the good reasons why it's possible to generate a lot of torque. But then later on we'll talk about the AC motor, which is a very, very powerful motor that we use to generate a tremendous amount of torque. In fact, that amount of torque is so huge that SMRT uses PMAG, or your AC motor, to drive the train. So later on after a break, we'll come back after the commercial break.